Section 2.3, looking at graphs, looking at limits graphically. So the first thing, you should have watched the video, and I'm going to just kind of go through this quickly, but stop me if you had questions, or if he went too fast and it didn't make sense. I'm going to try to clarify and clear things up for you. All right, and to answer Leonard's question, I have a little card that I put in my digital camera that I can record our lessons and then post them on our classroom page. So I have a video monitor too that the digital camera goes to. So trying to figure out all this stuff it's an adventure for sure. So first thing, a continuous function is a function that has no breaks or gaps in its graph. You can draw it without lifting up your pencil. That kind of makes sense. If it's continuous, you can draw it and you don't have to lift up your pencil. So if it's not continuous, it's called discontinuous. And if it's discontinuous, there are three types of discontinuities that we're going to look at. The first one is removable, kinds that you can remove. This is a picture when it has a hole in it of something that you can remove. It's a removable discontinuity because you can plug the hole. If you plug the hole, then you're able to keep moving and not lift up your pencil. So if you look at a removable discontinuity, you're looking for a hole. Non-removable is when you can't just plug a hole. It's just not that simple. And so this one, if I look at this discontinuity, I can't remove it. There's no little plug a hole issue. So this one is called a non-removable, and because the function goes towards infinity, whether it be infinity or negative infinity, it's called a non-removable infinite discontinuity. So non-removable infinite because it involves infinity and you can't just plug a hole. Or you have a non-removable jump discontinuity. That's where there's a jumper. It jumps from one place to another. I can't connect them. Just plugging a hole is not going to be enough for me to do. So it's called a non-removable jump discontinuity, and it's whatever the x value is that you come to where you've got that jump. So you're looking for a gap when it comes to removable jump discontinuities. So over in my margin, real quick, and if you want to, I said, just so I could remember, that holes are removable discontinuities. If the function goes to positive or negative infinity, it's an infinite discontinuity that's non-removable. And if there's a gap, it's called a jump discontinuity that's also non-removable. So that's kind of a quick summary of what all those pictures that he was talking about are to the right. So I will pause for one moment so you can copy that if you want to put that in your margin too. Okay. Then he went to doing some examples. So this picture has, if I skate along here, it has a non-removable jump, there's a gap, continuity at x equals -3. And then I keep going along and I can plug a hole. So that's a removable discontinuity at x equals 1. They were your two for that one. Then he went on to describe left-handed one-sided limits, left and right-sided limits. So let me give you the box first, and then I'll give you my margin notes. So a one-sided limit is the y value that the function approaches. Now this word approaches is hugely important in this section. So I'm going to not only highlight it, I'm going to circle it too. Because the deal is, it doesn't have to touch it. It just has to approach it, which is kind of interesting. So approaching is the real word there that's going to be important to us. A one-sided limit is the y value that the function approaches from either the left or the right side of a given x value. So you're looking to the left or you're looking to the right of a given x value. And the limit itself is the y value that the function, again that word approaches, at a given x value if the left-sided limit is equal to the right-sided limit. All right, then he gave some examples in that. Let me give you my margin talk here. All right, so here's what it looks like. Here's the way that they're going to write it. And if you watch the video, I'm sure you'll see in the next page where he goes with this. But you have limit, Lim, and then underneath of it, you have an x with an arrow, and then the x value you're looking at. So this one's looking at -3 with the plus sign of some function. That means you're looking at -3 coming from the right. Plus means from the right. If I'm coming from the left, then instead of me having a plus sign after the -3, now there's a negative sign. And that means you're looking at it as I come from the left. And if there is no sign after it, like my third example here, I'm looking at the limit as x approaches -3 and it doesn't say left or right, that means I have to check it from the left and from the right and make sure that they match. They have to be equal is what he's saying in the box there. So again, I'm going to give you a second to copy that into your margin or make a little note of that. And then we'll flip to the next page. Okay. So then he gives you a whole bunch of examples here that are talking about this same kind of thing. So if I'm looking at this first, number 2, I want to know what the limit is at 3. Well, 3 is right here. I'm going to put a dot there so I know what I'm looking at. And see how there's not a plus or minus after it? That means that it's a -3. That means that I need to look at it from the left and from the right. So I have these little arrows drawn. I come from the left, my y value approaches 4. If I come from the right, my y value approaches 4. And so my limit is 4 because they're equal. And the second piece here is asking you, what's the coordinate? This one's saying, do you have a coordinate at -3? If x is -3, what's the corresponding y value that would create the coordinate, which is where I put my dot here, and that would be at -3, 4. So the coordinate would be a 4 as well. That's when you just have a smooth, continuous graph that's happy and doing all its thing. Second picture has an open circle at that same place. Now, how does that affect it? So if I'm looking at this and I'm looking at how it could be affected, I'm at -3. The limit, again, they didn't give me a plus or minus after it, so I'm looking from the left and from the right and looking at what the y value is approaching. Again, the word is approaching, doesn't have to equal, which is what makes this a little confusing. So if I'm looking at this from the left, I'm coming up here and I'm getting closer to 4, it's approaching 4. If I'm coming from the right, it's also approaching 4. They're equal to one another, therefore the limit exists, it's 4. However, if I look at the coordinate, does the coordinate exist? And you've got -3, if I come up here, it's an open circle, so that's not included, that's not a coordinate, that's why it does not exist. You could also say undefined if you prefer, but it's a does not exist, DNE. Then I get to the third picture, and this is the same exact thing, except now I've got this random point down here. Open circle up at -3 up here, but closed circle down here. So let's check it out. Limit again, same exact idea. Come from the left, it approaches 4. Come from the right, it approaches 4. It's not equal to 4, but it approaches 4, therefore the limit's there. And if I look at the coordinate, can't be the open circle, but it can be the closed circle, so my coordinate is at -2. So -3 would be at -2 where the closed circle is. And then they change the graph up on us. So now I am taking the limit at -3. As I approach it from the left, I get 4. As I approach from the right, I get -2. They're not the same thing. They don't approach the same thing. My y value over here is approaching 4. My y value coming this way is approaching -2. Therefore, it doesn't exist. The limit doesn't exist. The coordinate does, though. If I look at -3, closed circles down here at -2, there it is. Last picture. Limit at -3. Again, if I come at -3 from the left, it's approaching 4. If I come at -3 from the right, it's approaching -2. They're not the same. They're not equal. So there is not a limit. Doesn't exist. But there is a coordinate. There's a closed circle at 1. So my coordinate is -3, 1. All right. I'm not seeing any questions. We good to go on? So here's what my note was in the margin over here to be aware of. If I'm looking at this set, and you'll see this in the practice problems we're going to do in just a second. If I see these different notations, some are from the left, see the little negative sign afterwards, little plus sign afterwards, some are from the right, and then some don't say anything at all. So that means I have to check left and right. But then I get down to like an I, letter I here. That's asking you for the coordinates. So I said, watch out, little warning. Some are limits and some are coordinates. You got to be careful of what he's asking you for. So watch with your notations here, which ones are coordinates versus which ones are limits. Now I don't. Okay, so here's the deal with the does not exist for limits. Actually, you know what? Hold on to that question for 1 second. Let me talk about A, B, and C, and you'll see. I think you'll see it'll clear up what you're asking me. So I'm going to move on with a couple examples here, and I think it'll answer that question about the does not exist that came up. All right, so first one. A, I'm looking at -2 from the left. Little negative sign after that is from the left. So here's -2. If I approach -2, if I'm coming out the graph up -2 from the left, here it is. What is the y value approaching? Well, the y value is approaching 1. So that's your 1 that's there. For part B, now it says, okay, well now come at -2 from the right. Well, here's -2. This was from the left. From the right's over here. This is approaching from the right, going that way. What does the y value approach when I get close to where x is -2, coming from the right, and it would be at -2. That's your answer for B. And then C is saying, all right, well, what's the limit at 2? In order for you to have a limit at 2, these two numbers have to be equal. If they're not equal, then the limit doesn't exist. So you'll see how there's a gap there? That kind of makes sense too. It's not approaching the same thing. Where, let me take you down to this picture real quick. If I approach this open circle from the left, I get 2. From the right, I get 2. Therefore, the limit exists. So this one is one where the limit would be 2, because from both sides, I end up getting the same y value that it's approaching. This one, it's approaching different y values, and that's why the limit doesn't exist. All right. Ask away more if you need more clarification on that. This one is, what's the limit at 1? If I'm at 1, I come from the left, I get a y value of 1. If I come from the right, I get a y value of 1. So my limit's 1. If I go to 0, from the left is -2, from the right is -2, I have a limit because they're the same. This one is asking me just for where, approaching 3 from the left. So 3's over here from the left, would be coming this way, and that would be this value of 5 that's up here at the peak. If I approach -1, -1's right here, let's go down. From the left and from the right, it's this y value of -3. That's G. If I approach -3, here it is, -3 from the left and from the right, it's 0. And this is a coordinate. Now we're into coordinates. So coordinate -2, where's the closed circle? It's at 1. If I'm at 1, where's the closed circle? It's down here at -2. That is number 3. And number 4, true or false? I have the limit at -1 from the right. -1 from the right equals 1. That would be coming this way. So it equals 1, and that's true. The limit of 2 at 2 is 2. We kind of talked about that a second ago. As I approach 2 from the right and from the left, they equal the same thing. So that would be 2, that's true. If I approach 1 from the left, 1 from the left would be this guy. It equals 1, that's true. Again, open circle, it doesn't have to actually equal it, it has to approach it. If I approach 1 from the right, 1 from the right, that would be this guy, and that would be a value of 2, that's true. The limit at 1 doesn't exist because this is 2 and this is 1. They're not the same, so it doesn't exist. 0 from the left and 0 from the right. 0 from the left is 0. 0 from the right is 0, so that's true, they are equal. The limit as x approaches 2 doesn't exist. That is false because both sides, both approach 2 whether you're coming from the left or from the right. All right, we're going to try some on our own in just a second. There were 3 things he clarified at the end very quickly. He said in order for a function to be continuous, there's 3 things that have to happen. You have to have a coordinate at point C. Let me show you my little picture over to the side here. You have to have a coordinate at point C. All right, I got a coordinate there. You have to have the limit that exists at C, whatever that x value is, and the 2 things have to be equal to one another in order for it to be continuous. In order for you to be able to draw it without picking up your pencil, the limit has to exist from both sides and the coordinate has to be there as a solid point. Whew, that was the notes. Okay, let's try some examples together. See if we can clarify this. So again, I just randomly picked a few problems. The first one I'm looking at is number 3. And number 3 says identify the x values of each discontinuity and write if it's removable or not. If it's non-removable, then classify the type. So remember, we have 3 kinds of discontinuities. There's the one that's the whole. That's a removable discontinuity. There's the one that's got where the graph goes to infinity. That's a non-removable, if I can speak, non-removable infinite discontinuity. Or there is a jump in the graph, and that is called it's non-removable as well. So it's called a jump discontinuity, and it's non-removable. Here goes. Number 3. So you're skating along the graph, and you're looking for the first thing where you first have to pick up your pencil, right? So I'm looking at this. It goes to negative infinity this way, comes here, and then I stop. And then in order to continue on the graph, going from left to right, I've got to jump up to this place here. So is it just a quick hole that I can plug, or is it something that I've got to navigate over? And it's obviously going to be a big gap between the 2 things. That's a non-removable jump, because I got to jump to get there. Discontinuity, I'm going to abbreviate that, disc, at x equals, all right, well, what is the x? So it's at negative 3. So that's going to be the very first one I come to. That's this guy. Got to jump to get to the next part. Now I'm going to skedaddle down my graph a little further, right? Keep going until I get to this place where I've got to pick up my pencil again. This one is a hole. But see how on the other side of it I can keep going if I can plug that hole? That's the one that is a removable discontinuity, because I can just plug that hole and keep moving. So removable discontinuity, and that one occurs at x equals 1. That takes me to here. There's more graph for me to follow. So now I'm going to keep going, and I get to this place where x is 2. Well, when I get to x is 2, I have to pick up my pencil, and I got to come up here, and then I can continue on my graph. So if I'm looking at this guy is going to be you've got 3 choices. Can I plug the hole and keep going? And the answer is no, because I've got to jump up to get it. So this one's another non-removable jump. All jumps are non-removable. Non-removable jump, discontinuity at x equals 2. And then when I continue on, I can continue on and never pick my pencil up again because it's going to infinity. Of your 3 pictures, there's only one that has this particular problem did not show you an infinite non-removable discontinuity. You will have one over here in number 2 because that's where you have an asymptote. And see how the graph goes to infinity on either side of it. So this would be an example that shows the non-removable infinite discontinuity, which is not seen in the one that we just did. All right, got the idea of the 3 types of discontinuities? No questions in the hood. Let's go to number 6. So number 6 is, again, giving you mostly limits that they're asking you about. There are a couple coordinates that they're asking about. Maybe let's do the coordinates first so we get them out of the way. The coordinate, this one is a coordinate question for part B, f of 1. what is the y value at 1? So I go to 1, I look at the y value, and it's an open circle. So I say there is none. There's no closed circle there at 1. So this one does not exist. It's this open circle down here, and I don't know what I don't know what that is. Can't include it. All right, I'm going to go to the next coordinate. That's this one at 3. If I'm at x equals 3, what's the y coordinate? Well, it's at -1, and there's no open circles there, so it's happily -1. And then I'm going to go to -2. I'm over here. Oh, there's a hot mess at -2. Check him out. So I'm looking for what the coordinate is, though. So the coordinate is where the closed circle is. Closed circle is 3. That would be h. So finding the coordinates, open circle, closed circles, I think you guys have that. That's not a big deal. Then we're into this new stuff with limits. So they want to know, what's it doing at -3? So I come over here to -3, and I look at -3 coming from the left because they didn't tell me with the little plus sign or minus sign after it which way I'm going. So I have to check both ways. So from the left I get 0. From the right it's approaching 0. Therefore my y value is 0. And that's going to be my limit because they're the same from the left and from the right. I'm going to see, what's it doing at 1? Here's 1. If I come from the left, I'm over here. If I come from the right, I'm over here. And I'm looking at what the y value approaches. And it's approaching from both sides, it's approaching a -5. So my limit for this guy is going to be a -5, even though there's an open circle there and the y value actually does not exist. It's what's the y value approaching from the left and from the right. Then I get a 1y1. This is -2 from the right. Find -2 and come from the right. Now this can be, let me erase these ones I had here before. This can be a little confusing. So if I'm at -2 and I'm coming from the left, it's this way, coming from the left at that point. If I'm coming from the right, guess what? I'm over up here in this neighborhood. I'm coming at -2 from the right. So I'm up at this high point, which is at 4. And the question is, what is the y value approaching from the right? It's not what it's equal to, it's what it's approaching. It's approaching 4. Brings me to F. What is -2 approaching from the left? Well, that's this little piece down here. From the left, it's going towards this y value, approaching this y value of 1. That's F. And then we're looking at G. So what is the actual limit at -2? Well, at -2, I'm checking it out. -2, one of the values was 4, one of the values was 1. They're not approaching the same y value, which means that that limit can't exist. So this is another does not exist. They have to approach the same y value or else it doesn't work. Then I says, okay, well, what's the limit at -1? So if I'm looking at what it's doing at -1, here I am at -1. Let me erase this guy from up here. He had some really cool yellow highlighted things when he was doing the video with you. Let's see, -1 is here. I'm going to answer questions in 1 second. I'd be coming from the left going this way and from the right going this way, and that puts me -1 right at this coordinate, which is at 3. So I is at 3. And the question is, how do you know if it's coming from the left or from the right? It's this little sign that's even actually kind of hard to see right after the number. The negative means from the left, and if it were a positive, it means from the right. So that's how it's telling you which way you're going. So this one in J is coming from the left. I want to know what it's doing at 1. Here's 1. Coming from the left. That would be coming this way. And if I'm looking at what the y value approaches, I'm over here at -5. Now I kind of was talking fast through that, so I'm going to take a second and see if you have any questions up to there. Next thing I'm going to do is set you free trying one. See if you're ready. Okay. All right, so I want you to try number 8. See if you can do number 8. Here it is. pipe up in the chat with any questions or unmute yourself if you get stuck as you're going through. Number 8 is in the practice problems after the notes. I have it on the screen. If you don't have it printed out, you can just look at the screen and see if you can answer them.
I was looking at my thing and I was doing these ones with you, the 6, but I wasn't seeing 8. That's fine. I'll just write it on.
Yeah, it was the next page, actually. It's like there was a page after that, so it's on the next page. You said you had up to 6, so it's the next page stuff. But yeah, just you can check it out from the screen. Although it's kind of hard to see the pluses and minuses of these little things, but... Yes, Maddie, before we sign off, make sure that I go back and look at number 2 with you. Yeah, that's a whole hot mess, number 2. How about if you are done, you tell me you're done in the chat? Thank you. Thank you. Yeah. Okay. I'll give it just another minute then. All right, let's see how you made out. So for 8A, it should be 1. B's over here, that's a coordinate, that should be 1. C is 4. D is 1. E doesn't exist. F is 1. G is 1, whole lot of 1s. H is 1. I is 2. And J doesn't exist. All right. Tell me in the chat which parts you want me to talk about. C. So I'm looking at the limit at 2. Now notice it does not have a right or a left with it. So it's 2. I got to check both ways. So here's 2. If I come at 2, I can't even come at 2 from the left because see how there's a gap here? There's nothing on the graph. There's no solid line to the left of 2. So I can't even come at 2 from the left. There's a problem there. If I come from the... Oh, wait a minute. My bad. Up here, right? So I'm looking at my answer going, wait a minute, I have an answer there. If I'm coming at 2 from the left, then that's this piece here. So that's approaching 4. If I come 2 from the right, that's going this way, up towards it. That's also approaching 4. And that's why the limit is 4. Were you caught up like I was caught up looking at the, maybe at the coordinate for part C, rather than looking up where the actual graph is?
Okay, yeah, thank you.
Yeah, I'm with you on that. It stumped me too for a minute. J, the limit at 1. So here's 1. I want to come from the left. Well, that's 1. If I come from the right, that's up here. That would be 4. And see how they're not the same y values? It's not approaching the same thing. So that's why J is it doesn't exist. I think this extra little dot here is kind of confusing. You almost want to ignore that guy unless it's a coordinate question. Anything else for 8? All right, the challenge question I was going to give you is on the extension sheet. I'm going to save that for another day. It's going to be this number 3, and I'll let you ponder this for a bit. You're going to have to sketch a graph that has all of these qualities. But I'm going to save that for another day because that'll break your brain. It's a really challenging question, and I don't want to break you quite yet. I'm going to do 2 things. First thing I want to do is remind you of what's due and where we're going next because we just finished the notes for 2-3. So this is what you need to do for Monday and Tuesday till I see you again on Tuesday. So, and I'll post this as well. But these worksheets are all on our Google Classroom page already. So there's you're working on the practice problems 1 through 9. They're due on Monday. The review sheet is due on Monday so that we can take answers or we can go over whatever questions you have on the review sheet or on this assignment before you take the quiz on Tuesday in class. When we meet again on Tuesday in class, there's a quiz. On Monday, you have these 2 assignments due. And then I'll post the rest of it as we go. Oh, there's a question on F. I will go back to that. So if you are, you can sign off if you are good to go. I have 2 things I'm going to go over with anybody that wants to stay, and that would be number 8F and number 2 from the practice problems that people requested. All right, so I will see you on Tuesday. Email me with any questions. And, okay, so Ava's good. I'm going to go over number 2 then from the practice problems if you want to stay. If not, I'll see you Tuesday. Is the review sheet called, it's actually called Review 2-1 to 2-3. I have not posted the review sheet for the whole section yet. Hold on. Yes. Let me get a couple things here. I need to write myself a note for Miss Bella. Let me do that. And hang on a sec. So no, just hang in there for just a second, and I will. I'll catch up with you. No, do you have it handy? If you turn on your camera real fast, I can get you out of the way so you can do your thing. And then we're going to number 2 for the rest of us that are staying on. This was the question. Oh, I gotcha. Yep. All right, you are good to go, Sir Noah. Here comes number 2. There are 3 kinds of discontinuities. The first one is if you can plug the hole, it's called a removable discontinuity. If you are non-removable, there's 2 types of non-removable. The first one is a jump, and the second one is an infinite discontinuity. So 1 removable and 2 non-removable. And what you're going to do is you're reading along the graph until you have to pick up your pencil. That's the whole idea. So if I'm on the left side of this, I come along, I'm skating along, I'm happy till I get here, and I'm like, oh my goodness, I got a hole. So I'm looking now if I can plug the hole. If I can plug the hole, then I can keep moving. That's called a removable discontinuity. So this guy has, the first thing that you come to is a removable discontinuity. At x equals, my x value is -2. That takes me here. Yep. If you need to go, you can go, but I'm going to real fast finish this for the person that asked. Then I get to this place. Now I've got to jump to get to the next place. So this guy's going to have a non-removable, you can't remove jumps, non-removable jump at x equals -1. Takes me here. And now I'm going to infinity. Well, I have to pick up my pencil if I'm going over that line where the asymptote is. So that guy's going to be a non-removable infinite because it's going to infinity. Discontinuity at x equals 2. All right, so for my person that wanted number 2, there you go. And we can take more questions on that when I see you again. So email me if you've got any questions or problems, and I will see you on Tuesday, being quiz ready. All right, have a good day, have a good weekend.